Hello, here in this video we are going to discuss electric potential at any point due to a uniformly charged thin spherical shell. By thin spherical shell you need to understand that it is hollow from inside and it is uniformly charged. So when we consider such a shell, suppose here in the diagram you can see, let this be the charged shell which is hollow from inside and it has a radius given by capital R. Now there may be three different points where we are going to find the electric potential. Let the point be given by P if the point can be outside the sphere, at the surface of the sphere, and somewhere inside the sphere. The small r represents the distance of the point P from the center of the sphere. So we are going to discuss these three conditions. Now the graph which you see here is, you can see here we are going to derive this relation here. When the value of distance from the center, which is given by small r, when the value of small r is less than or equal to r, the value of v remains constant, and that constant value is this. When the value of small r is greater than capital R at this region, that is outside the sphere, the potential decreases exponentially with the distance. So let us understand this. First of all, we are going to take a point P which lies outside the shell. If the point is outside the shell, suppose this is the point, we are choosing a point outside the shell, then this shell will simply behave as a point charge situated at the origin, because we have done the expression for electric field, finding an electric field outside a sphere which is hollow from inside, and we have seen that the sphere behaves as a point charge placed at the center. Same will be the case for potential also. So if you consider at a distance small r outside the shell, the value of electric field will be given by the same formula, 1 by 4 pi epsilon naught Q by R, where Q is the charge which is total charge distributed on the surface of the sphere, which is considered to be at the center. In this, where the small r, because the point is outside the sphere, the small r is greater than the radius of the sphere, so we see that v is inversely proportional to r, so a negative exponential curve is here. Now look at the second condition, where the point P is taken on the surface of the sphere. So in that case, in this formula there will be a change, small r will be replaced by capital R. So we have the formula 1 by 4 pi epsilon naught Q by capital R, where the value of small r is equal to capital R. So you need to understand that the whole charge, when we consider the point at the surface also, it behaves as if the whole charge is concentrated at the center and the distance is capital R. Now after this, we are going to discuss a point which is taken inside the sphere, where the value of small r will be less than capital R, that is the radius of the sphere. Now you need to understand one thing here. We will have the same relation which we are having at the surface, a point inside the sphere also we will have the same value. The reason, let me explain it. In the previous video we have just discussed that how electric field is linked with the potential. E is equal to minus dV by dr, like dV by dr. Now we all know for a conducting sphere which is hollow from inside, the value of electric field inside is always 0. So if electric field is 0, then dV by dr is 0, which means V is a constant quantity. Potential here is a constant quantity. It means whatever potential is there at the surface, at any point inside the sphere, it will always remain the same. That means the potential at the surface, it is given by 1 by 4 pi epsilon naught Q by capital R. It remains the same inside also. You consider any point inside the sphere, the potential doesn't change, because we know dV by dr is equal to 0, which means V is a constant quantity. Whatever potential was there at the surface will be inside also. So a straight line here shows that the potential doesn't change with the distance from the center if the distance is within the radius. But as one moves out of the sphere, the distance here increases, and when the distance increases, now the potential from this point goes on decreasing exponentially, and it is given by it is actually inversely proportional to the distance r. So I hope this is clear, and this is very important also in numericals, and in the next topics you will get the concept of this. You have to use the concept of this. So I hope everything is clear to you. You have to inform me if you have some doubt, and I also want that if you have gone through and if it is clear also, then also you need to inform me.